So as a step 2, the next step is to select a displacement function, which we have already done so, but nevertheless we will follow the standard procedure. We will select the displacement function. So now displacements, that is a function which describes the displacement within the element, is again given by, since there are 8 degrees of freedom, we have 8 terms defined in the column matrix, which is related by nothing but the typical shape functions which we have already defined. So the step 3 would be the critical step now, is to define the strain displacement as well as the stress strain relationships. So by now I hope you have a clear idea as to where we are getting. We want to obtain the B matrix, which relates the strains to the displacements. We would like to get the D matrix, the constitutive matrix, and of course, with the help of other geometrical parameters, the thickness, maybe the area of this element, plane element, we can derive the stiffness matrix. We can evaluate the stiffness matrix. So for that, we need to, this is the intention of trying to find the relationship between the stresses and displacement as well as the stress strain relationships. We already know that we want to formulate element matrix, that is B matrix, to evaluate the stiffness matrix, that is simple K matrix. We already saw that it becomes really tedious to express the B matrix in terms of the X and Y coordinate systems. So now we have a more elegant method. What we have to do is we have to formulate them in terms of an isoparametric coordinate system, that is using the natural coordinate system. So eventually this may seem quite tedious, but in terms of the implementation, complete implementation perspective, this formulation becomes really easy, and especially for performing integration, this becomes really quite easy. So in order to construct the element stiffness matrix, first we have to determine the strains. So what are strains? How can we express the strains? The strains are nothing but the derivatives of the displacement with respect to X and Y coordinates. That is, we would like to obtain W by WX and W by WX. Similarly, we would like to obtain these terms in order to express the strains. The displacements here, however, they are now functions of the natural coordinates. That is, they are functions of S and T. So with the help of the shape functions, we could now determine how they change with respect to the X and Y coordinate system. So in order to get an idea, before we go ahead with this, let's try to define a function f, which represents the displacements as a function of u and v. So in order to express these functions, that is u and v functions, which are now coordinates, which are functions of natural coordinate systems, let's try to apply the chain rule and try to extract the relevant information which we would like to obtain. So let's define an arbitrary function f, which is a function of u and v, and we would like to obtain the derivative of function f with respect to s, because now it is because the function f is defined using u and v. So we can apply the chain rule in order to express f function, since we are interested in defining the strains in the element. So we have applied the chain rule here. Similarly, we have to differentiate, or we have to get the partial derivative with respect to y and partial derivative with respect to again s, because we have already found the relationship. So now in this equation, these terms are all knowns. This f by s term is already known. We know the relationship because we already know the relationship between the shape function. We have obtained the shape functions are described using natural coordinate system S and T, and we already know the relationship between the displacements, that is U and V, with respect to S and T. So we already know da bar F by da bar S. Similarly, we know da bar F by da bar T. These are known factors. Since we use the same shape functions to describe the shape of size and shape of the element, we already know the relationship between the, because we have already done the mapping, we know the relationship between the X and S coordinate system, that is the global coordinate system and the natural coordinate system. So we already know this derivative, da bar S by da bar X, da bar Y by da bar S, da bar X by da bar T, and da bar Y by da bar T. We already know all these factors. So what we're trying to obtain is this, the strains, particularly these strains we want to extract, because this is what we are interested in. In order to express the B matrix, we need the strains. So because we know the strain in the X direction is nothing but W by W X. So since F can be any function here, it can be U or it can be V. So we need these values in order to, we need to evaluate this in order to obtain the strains. So for extracting da bar F by da bar X and da bar F by da bar Y, we use the Cramer's rule. So this includes the calculating determinants. In the references, in the Logan's book, you can find a detailed explanation as to how the Cramer's rule can be applied for evaluating the determinants. I will write down the equations for saving time for the continuity of this. We can use the Cramer's rule and express the terms which we are required the form by expressing some determinants. When we apply the Cramer's rule, you would end up in getting this relationship, the determinant in the numerator, and as well as there's a determinant in the denominator, which has to be evaluated for evaluating these two terms. Similarly, for da bar F by da bar Y, you can express this. You can evaluate the determinants in the numerator and the denominator and obtain the relevant results. So the evaluation of the determinant in the denominator is equivalent to calculating the Jacobian matrix, which is given by Jacobian is nothing but, as you can see, the denominator terms are the same for both da bar X, da bar F by da bar X, and da bar F by da bar Y. So the denominator is nothing but the determinant of da bar X by da bar S. J is the Jacobian matrix. Now we need to find a relationship to get to the required B matrix, isn't it? We know we can express the strains and relate it with the displacements, and this relationship is given by the B matrix. We already know this. Let's call it 7.3.11. And we know the B is expressed now as a function of S and T. What we can do is, in order to establish the relationship between the strains and displacements, we can use an operator matrix since these functions are expressed as a function of, since the B matrix need to be expressed function of S and T. So what is the strain matrix we are interested in? Sigma X, sigma Y, and since this is a plate element, there will be also a rotation, shear strain coming into play, which is related by the displacements. So this is the epsilon matrix, this is the displacement matrix, and the B matrix can be expressed such that displacement, the strains in the X direction. If you multiply these two matrices, you will realize the strain in the Y direction and the rotation term is nothing but a summation of these two. On the right hand side, this matrix is called an operator matrix. That is, these terms, they represent the partial derivatives of any variable we put inside this bracket. It's what we call an operator matrix, a du or a BV. And this is the operator matrix we describe. Our next task is to evaluate this matrix so that we obtain the relationship between, we obtain the B matrix. So using equation 7.3.9, this is nothing but this relationship where we have delta F by delta X and delta F by delta Y using this equation. So using the values that we have obtained and evaluating the determinant in the numerators, that is on the top part, what we get is the Jacobian, which is sitting underneath, of course, the Jacobian minus W by S, the operator term. Similarly, the operator Y can be expressed. What I have done is nothing new, but substituting or evaluating the numerator in the equation 7.3.9. We know J, the modulus of J, that is the determinant of the Jacobian, can be obtained. And with the help of equation, these values, that is using 7.3.13, in equation 7.3.12, we do a simple substitution. What we get is, we can express the strains now in terms of the natural coordinate system. We'll write down expressing strains using the natural coordinate system. The strains in the x direction, y direction, as well as the shear strain. Simple substitution. This equation now, here, since we have already evaluated the operators, or obtain expressions at least. Let me try to write it again here. Mind you, on the right hand side, it is U and V. So for the shear strains in the y direction, we have only delta V by delta X, which can be expressed. Delta V by delta Y can be expressed delta X by delta operator, any term minus delta X. So for the shear strain term, we already have W by delta X plus delta V by delta Y, these two terms. So we have to include this. There will be two terms. The first term is delta S. Second term here. Yeah, so the next step is to express the shape function again, because we would like to express the B matrix in terms of the shape functions. We can using equation 7.3.7, which describes the relationship between the displacements with the shape functions. We can express equation, the equation which we just wrote, that is 7.3.14, using the shape functions in the global coordinates form, as the strains is nothing but the dash matrix times the shape functions D. You can see that the B matrix has been split into two matrices, D dash matrix and the shape matrix, that is the shape function matrix. So the D dash matrix is nothing but, I will write down again for you to be clear. For it to be clear, this is the second term, yeah, operator. And the final shear strain terms has two terms, delta X by delta S, operator times delta T minus. Second term here, I will write down, because to save some space, because I don't have any space there. We have defined the B matrix and splitted them into two, such that we separate the shape functions and also obtain a D dash matrix. So we know the B matrix is a 3/8 matrix. So meaning the D dash matrix is a 3/2 matrix. So in order for the rank to be equivalent, the N matrix should be 2/8 matrix. What we have done is we have expressed B now as a B matrix as a function of the natural coordinate system, meaning as a function of S and T. So what we have is we have strains in terms of S and T. We know the explicit form of B can be obtained by directly substituting this D dash, evaluating D dash using equation like 7.3.5, where we express the shape functions. So the explicit form can be obtained by direct substitution and also by corresponding matrix multiplications. The P as a function of S and T can be now described using this matrix by using equation 7.3.17 by substituting equation 7.3.16 for D dash, by substituting 7.3.5 for obtaining the shape functions. Can be these two can be substituted in equation 7.3.17 and obtain the explicit form by performing the matrix multiplications. I will not go into these details, but it can be expressed or separated into submatrices. So all these formulations are implemented, of course, in the computer program. The B matrices, I have once you do the multiplication, you would obtain the complete B matrix, which can be expressed using submatrices, where submatrix of B can be given by PI submatrix. Here I use the following notation. Whenever there's a term like this, if I write down now N1, S, it means that there's a differentiation that indicates with respect to the particular variable. N1, S term refers to differentiation of N1 with respect to S. N1, S. Okay, so if you see when I write N1, S, it means it's differentiation. You take the partial differentiation of the N1 variable with respect to S. Each submatrix, B-ith matrix, because we have 4 matrices, B1, B2, B3, B4. B-ith matrix can be expressed in terms of A times Ni, S, meaning it's the differentiation of the ith function with respect to S minus B Ni, T, 0, C Ni, T, S, C Ni, T. So here, I is equal to 1, 2, 3, and 4. And A's, I have introduced A, B, C, and D, and this is equal to Y1, S minus 1, Y2, minus S minus. Similarly, B, mind you, if I make a mistake, just correct me even later onwards. Seven, 3, 19, 7, 3, 20. And using the shape functions, of course, we know N1, S is equal to 1 over 4 T minus 1. N1, T is equal to 1 over 4 S minus 1, and so on and so forth. You see, these are quite lengthy expressions. We eventually need the help of a computer to solve such functions. And the next task is to find the determinant of J, the Jacobian. Of course, this is also a complex task. Especially, we can use the equation to simplify the process. We can use equation 3.10. Yes, which is nothing but the expression of the Jacobian 7.3.10 for evaluating J. And of course, equations 7.3.3 for X and Y, we can evaluate J. J would be equal to 1 over 8 times 0. Now the derivatives have been evaluated. T minus S, S minus 1, T minus 1, S minus T. 1 minus S plus T, S plus 1, 0 minus T minus 1, minus S minus T times YC, where XC transpose is equal to X1, X2, X3, and X4, and YC is equal to nothing but Y1, Y2, Y3, and Y4. All right, now we have already done the hard part. We have obtained the Jacobian, the determinant of the Jacobian as a function of S and T. You can clearly see that now. We have obtained J as a function of S and T, as well as the known global coordinates, which are X1 to X1, X2 to Y up to Y4. We have expressed the Jacobian with the nodal coordinates. Since B is a function of S and T, we can evaluate the numerator and the denominator using the known global coordinates X1 to XY4. So the stress strain relationship again now, you can see, is sigma is equal to constitutive matrix, which includes the properties of the materials, the B matrix, which is nothing but describes the shape, the displacement, which has been multiplied by the D matrix. So because B matrix is a function of S and T, the strain matrix now will also be a function of S and T.